So when we first started talking about momentum, we talked about that it relates to mass and velocity, but it also has something to do with force, right? If I have a huge big object with a lot of momentum traveling really quickly towards me, it's going to take a lot more force to stop that object than it would to stop an object that's going really slowly. But if you think about that, in fact what I could do is I could apply a small force to the large object and just apply that force for a really long period of time. Eventually it would stop. So force and time are somehow connected. I went through the following derivation in the original momentum video. I'm going to do it again here. So we know that force is equal to mass times acceleration. And we know that momentum is equal to mass times velocity. So if we want to connect momentum to force, how do we do that? Well, we know that velocity and acceleration are connected because acceleration is the change in velocity over change in time. So we can say that force, then, is equal to mass times delta V over delta T. And this here is just change in momentum, right? So we can then write that force is equal to change in momentum over change in time. And if we want to solve for change in momentum, then we have that the change in momentum is equal to force times the change in time. So this we've already seen once, and this actually has a name. In fact, if you think back to work and energy, write that up here, you remember work is equal to the change in kinetic energy, and work is equal to force times time. Displacement. I'm jumping ahead of myself here. Impulse is equal to the change in momentum. And impulse is a vector, since change in momentum is also a vector. And we can say that impulse is equal to force times time. So this is actually what we did with almost all the work equations, right? When we had work and energy, we would take the change in kinetic energy and set it equal to force times distance, and then we could solve for whatever it was we were looking for. Same kind of idea with impulse. This I is called impulse. And it's because what it says is, if I want to produce a change in momentum, I have two options. If I want to produce a large change in momentum, I can either apply a large force for not too long of a time, or I can apply a not so big of a force for a really long period of time. A great example of this is I can slap my face, or I can push my face, and I can produce the same change in momentum. Here, large force, small time. Here, small force, large time. Right? So let's look at how we use this to solve actual problems. So the setup is not super different from how we would do work and energy. So I'm just going to write up here, impulse is equal to change in momentum, and impulse is equal to force times time. And let's say, for our problem, let me find one, let's say we have a block of mass m moving to the right with the speed of v0. And let's say it encounters a surface with kinetic friction, or with friction, sorry, and a coefficient of kinetic friction of mu sub k, and this extends for a distance of d. And I want to know how long does it take to cross this surface, to cross just the part with friction. So if you look at this, immediately there's no clear way to do this. If I just want to find time. So if I want to find time, I need momentum and I need force. So I have the force. I know what force acts as it goes over, the force of friction, but I don't know what the change in momentum is going to be. I need to find the velocity when it gets to the end. But if I need to find the velocity when it gets to the end, this just turns into a work problem. I have velocity, I know what velocity it starts with, I know how long it is, and I want to find the end. So this is a work problem, and then we can use the velocity that we get from work to calculate the change in momentum. So let's go ahead and do that. So initial kinetic energy is equal to 1/2 mv0 squared. Final kinetic energy is equal to 1/2 mvf squared, where vf is what we want to solve for. And we know that the work being done is negative mu k mg d. So setting this up, we have that work is equal to the change in kinetic energy. So negative mu k mgd is equal to 1/2 mvf squared minus 1/2 mv naught squared. So we can cancel out all the m's, we can multiply through by 2, and then we'll just add v naught squared to both sides. And we have that vf, also going to take the square root, vf is equal to the square root of v naught squared minus 2 mu k g d. So this is our final velocity. So now that we have our final velocity, we know what our final momentum is going to be. Our final momentum will just be m times vf, where vf is this. So let's go ahead and solve that. So now we're going to set up impulse and force and time. So our initial momentum, instead of our initial energy, our initial momentum is mv naught. Our final momentum is mvf, where vf is the thing I have down here. And, where am I? Force times time is negative mu k mgt instead of d. Very similar to work and energy though. So now we're going to set this up, set the two equal, just like we did over here. So we know that change of momentum is equal to force times time. So we have change of momentum is mvf minus mv naught equals negative mu k mgt. And solving for vf, sorry, we want to solve for t. Still divide through by m. So now we're going to divide by mu k mg. So then we have that t is equal to vf minus v naught over negative mu k gt, sorry, mu kg. And this negative sign we can just get rid of by flopping the signs on the top, flipping the signs on the top. So we have v naught minus vf over positive mu kg. And to write this out in its full form, which we found over here, the time it takes is going to be v naught minus the square root of v naught squared minus 2 mu k gd divided by mu k g. So kind of a tricky, a bit longer multi-step problem to try to solve. But again, when you know you're looking for the time, you want to use impulse. And to use impulse, you need to change momentum. So how do we find change momentum? To do that, we need to find the final velocity, because we know the mass and the initial velocity. So it's kind of just a working backwards thing from what you want to what you have. You could also say that, yeah, you could solve this using kinematics. You could calculate the acceleration, you know the distance, you know the initial velocity, you want time. You can set that up too. It's just nice to do with work and impulse because it's simpler. There are fewer chances to make mistakes, and often it will make problems easier than they would be with kinematics. So that is how you use impulse and what impulse is.